So this is the LeetCode problem 62, unique paths, also commonly known as the robot problem. This is one of my favorite dynamic programming problems, and so I wanted to use this one to kind of generalize how to approach dynamic programming problems. And so to start with, I mean, first it would be helpful to know what dynamic programming actually refers to. And so a dynamic programming problem is a problem where you can break down the problem into subproblems, and by solving all of the subproblems, it leads you up to the ultimate solution you're looking for. And so they're usually broken down into either top down or bottom up. And so bottom up is tabulation, and top down is memoization. And so just to start with, like, this one is a tabulation problem, and so usually it means you're filling out a table, and so you're usually creating like a table or a matrix called DP, and then you're filling out the table, and as you get to the end, you get to your answer. The memoization version is the top-down one, and that's where you're essentially starting at the end, and by recursively going through the function, you're building up to the answer in the same way, but you're also storing values to minimize the number of recursion calls that you have to do. I'll show a quick example of a memoization problem at the end. But when it comes to like breaking down a dynamic programming problem into its sub-problem, it usually involves like some type of like mathematical trick. And then once you figure out how to do that, all you're doing is iterating through the rest of the problem to fill out the table, like in this case, and then your answer you will have at the end. And so to kind of quickly show you how you do it in this one, I'll switch to this. And so you should note that if you notice in the code, technically the matrix that was made would have ones in every slot. I just left these out so you can kind of see what would get filled in, but these technically would all start out with 1, and then you would replace them with what the actual values are. But so just to kind of quickly help you see like the trick that you would employ and how you actually solve the sub-problem, we could kind of go through these really quick. And so like if this was the final block, like if it was just 2 by 2, you could see that the total number of paths to get to the square would be, you could go to the right and then down and then down and then to the right. And so you should know that the robot can only go down and to the right. It can't go left or up and or diagonally. And so like real quick, we could put a 2 in here. Whoops. And so now for this one, without kind of revealing how you would solve it like programmatically, like you can kind of just intuitively see that you could go all the way over here, you could go this way, and then to right, down, right, and then you can also go down, right, right. So you can see that there's 3. And so what you should potentially be able to notice is that whenever you're looking at a square, you can determine how many total paths to get to that square by adding the total paths that got to the above square and the total paths that got to the square to the left. And so you can see that this one would be 4, and then following that, this one would be 5. And so if you repeated this process, you would keep filling out all of these, and when you got to the end, this is your final answer. And so it would be dp of n-1 m-1. So that's the answer that you'd get to. And so you're iteratively going through all of these. It doesn't really matter if you go rows or columns first, but you're iterating through this entire table and building up to this answer. But the full solution really is just recognizing that you add the square above it to the square to the left of it. And once you know that, the rest is just iterating through the actual table. And so you can see, so also I should have noted too, I'll go back, the the first column and the first row index is 0, obviously. There's only one path that can go through them because it can't go left and it can't go up. And so you don't even need to include these. So there's no reason when you start the for loop, you don't need to index through the first row and column. And so you'd start here. And so that's why when you loop through, I'm starting at 1 for each of them. And then you can see I'm just setting the current square that you're in equal to, so this one is y minus 1 x, so that's the one above it. And this one is the one to the left of it. And so when you iterate through this, it'll fill out all those boxes, and then that last box on the bottom right gives you your answer, right? And so this is the bottom-up approach or tabulation. And so you're building up to the answer by filling out the table. And you can see, I've already ran this, and so you can see it's extremely quick because it's optimized for, doing the calculations as needed. Quickly, I wanted to show a quick example of the memoization or the top-down approach. And so we'll do, let's see, the Fibonacci sequence. Fine. So hopefully, if you're not familiar with the Fibonacci sequence, it's the first value is 0, the second value is 1, and then every value after that is equal to the sum of the previous two values. And so how it works from a top-down dynamic programming approach, it works so this dictionary is going to be where we're storing all the values, and we're storing them so that way we don't recalculate a value that we already calculated. And so we would look to see if in fib then return n if, so this is just defaulting because the first two values are 0 and 1, so if n is 0, it's 0, if n is 1, it's 1, and then this is where the real stuff is. And so we would do, so the result would be fib function of n minus 1 plus of n minus 2 see, what did I call it? Fib n. And so I can't run this obviously because this is I just put it at the bottom of the unique paths one, but what this is doing is that first it's checking to see if you've already calculated a value for the input. And so if you have, you should just look it up instead of recalculating it. Then obviously you're checking to see if it one of the default values of 0 or 1. And then if not, you're technically starting at the end, right? So when you plug in n, you're calculating the value of n minus 1 and then n minus 2, so you're recursively putting those back in, and then storing the results you get as you go. But so hopefully you can see that you're starting from the top because you're starting at n instead of building up to n, but then it recursively goes through all of the building blocks that would build up to calculating n, and you're storing the values so that you don't recalculate any ones that you've already done. And so this is the top-down version of a dynamic programming problem. But you can kind of see still that how you're turning it into sub-problems either by recursive function calls or by building up values in a table that ultimately lead to your answer. And so hopefully if dynamic programming problems have caused you hardship, this kind of helps it make more sense.